Hello everyone. Today we are going to explore a fundamental shift in the software engineering landscape from our topic containerization, a modern approach to application development. We will be understanding the basics, the benefits and its real world impacts. In the past decade, we have moved away from managing heavy physical servers and virtual machines to a new standard, containerization and orchestration. This isn't just a trend, it is the architecture that powers the modern internet, from Netflix to Uber. In this session, we will break down exactly what containerization is, why Docker became the industry standard, and how we manage these systems at a massive scale using Kubernetes. Okay, so let's start with the definition. What exactly is containerization? It is a modern form of OS level virtualization. Unlike traditional virtual machines and virtualization, which simulates hardware, containerization works by packaging an application's code together with all its specific dependencies, its libraries, binaries, and configuration files into isolated standardized units called containers. If you look at the diagram, you will see that multiple containers run on a single host machine. The critical technical detail here is that they share the operating system kernel. Because they don't need to boot a full operating system for each application, they are incredibly lightweight and efficient. The ultimate result of this architecture is that your application runs incredibly reliably and regardless of the deployment environment. But to really appreciate the solution, we must first understand the pain of the past. We call this the world before containers. We faced three distinct challenges. First one was inconsistent environments. This was known as the "it works on my machine" problem. A developer would write code that worked perfectly on their laptop, but it would crash in production because of a different library version or operating system patch. Applications behave differently across development, testing, and production. Second one was resource inefficiency. We relied on traditional virtual machines, VMs. Each VM was bulky because it required a full guest operating system to run. If you wanted to run three small apps, you needed three full OSs, which wasted RAM, CPU resources, and drove up costs. Third one was slow and risky deployments. Uh, Release cycles were stressful. Dealing with complex dependency matrices and manual server configurations made deployments slow and error prone. Now, when containerization as a technology came, it solved these specific engineering headaches with five transformative benefits. Faster deployments, where containers streamline the build, test, deploy lifecycle, which is the foundation of modern CI/CD, continuous integration and continuous deployment pipelines. Second one was portability. This is the concept of build once and run anywhere. The container abstracts away the underlying infrastructure, whether you are on a local Linux machine or a cloud server. The container runs the same way. Third one was inefficiency. We can achieve much higher application density on our servers. This leads to far better resource utilization and lower operational costs. Then stability, okay, scalability, sorry. When demand spikes, new containers can be spun up in mere seconds to handle the load. So it can also be used as a load balancing thing. Then at last, consistency. It eliminates the environment drift. If the code works inside the container, it will work everywhere the container is run. Okay, so now let's get technical and compare the architectures side by side. On the left, you see traditional virtualization. Notice the stack: infrastructure, then the host OS, then the hypervisor, which acts as a medium between the host OS and virtual machines, and then multiple guest OSs that suck up the system resources. The hypervisor's job is to emulate hardware. This means strong isolation but at a higher cost. On the right, containerization. A heavy guest OS layer is removed. Instead, we have a container engine like Docker that sits on the top of the host OS. The applications sit directly on the top of that. Let's look at the matrix table for a precise comparison. Abstraction layer. VMs abstract the hardware, whereas containers abstract the operating system. Overhead. VMs have a high overhead due to full guest OS per virtual machine. Containers, on the other hand, have low overhead because they share the OS kernel. Size. VMs are measured in gigabytes. On the other hand, containers are measured in mere megabytes. Startup time. VMs take minutes to boot. Containers start in seconds given that the engine, or the Docker engine as we say, is already running in the background as a process. Isolation. VMs offer strong hardware level isolation. Containers offer good process level isolation. This means that multiple containers can share resources of same hardware. Whereas in virtual machines, if a amount of RAM is allocated to a virtual machine, no other virtual machine can take like utilize that part of RAM. Okay, so while the concept of containers like Linux LXC existed for years, Docker was the platform that ignited the revolution. Docker is the open source platform that made containerization mainstream and accessible to average developers. Before Docker, using containers was complex and required deep kernel knowledge. Docker provided user-friendly tools to simplify building, shipping, and running applications, making it the industry standard. If you look at job descriptions today, companies from startups to major enterprises like Fast Financial, Monument, and Aquarium Learning list Docker as a key part of their technological stack. Okay. When we talk about Docker, we are talking about an ecosystem of five main components. A Docker file, which is the recipe, a simple text file containing the instructions for how to build your application image. Then comes the image, which is a blueprint, read-only layered template that includes your application code, libraries, and dependencies. From an image, you create a container, which is a live instance of a image. You can have multiple containers running from a single image. Then comes the registry, which is a storage library just like GitHub for Docker images. Docker Hub is the most famous example, acting like GitHub for Docker images. All this is orchestrated by the Docker engine, the background daemon that manages the containers and everything on your machine. Now we'll drill down the Docker image. An image is a portable file containing everything needed to run a piece of software. What makes it unique is how it is built. It is built from a series of read-only layers. As you can see in the graphic, we start with a base image like Python 3.9 in this example. Then we add a layer for dependencies like the requests library and etc. We add the app code such as the main.py file. This results in the final image. Each instruction in a Docker file creates a new layer, which makes future builds very efficient. These images are then stored in registries like Docker Hub. Okay, so how do we define these layers in an image? For that, we use a Docker file. It is a line-by-line script that automates the creation of an image. It defines the application's entire runtime environment. Let's walk through the code on the screen. From Python 3.9 Slim. This specifies the base image on which our main application will run. Work_dir/app. This sets the working directory inside the container. Copy requirements.txt. We copy our dependency file into the image. Run pip install -r requirements.txt. We execute a command to install those dependencies. Then comes copy dot dot. We copy the actual application code, cmd under bracket python and main.py. This provides the default command that runs when the container starts. For when you will interact with the Docker command line interface, here are some essential commands to get you started. Docker build -t my app. This command builds an image from the Docker file in the current directory and manages it to name it my app. The -t tag is used to name the image. Then comes docker run -p 8080:8000 my app. This runs the container from that image. The -p8080 colon 8000 part is crucial. It maps port 8080 on your host machine to port 8000 inside the container, allowing traffic to flow in. Docker PS. This lists all the currently running containers. Docker stop container ID. This stops a specific running container and kills it. So Docker makes managing one container easy. But in production enterprise environment, we face a new challenge, scaling. Running one container is simple, but managing hundreds or thousands of them is complex. We have to answer difficult operational questions, which are updates. How do you deploy updates without downtime? How do you automatically scale services up and down based on traffic? Resilience. What happens if a container or a server fails? Networking. How do containers discover and talk to each other? The solution to all these problems is container orchestration. The heading Container Orchestration brings us to the topic Kubernetes, commonly abbreviated as K8s. Kubernetes is the industry standard for orchestration. It is an open source platform that automates the deployment, scaling, and management of containerized applications. It was originally designed by Google, inspired by their internal Borg cluster manager. The name comes from the Greek word helmsman or pilot. Its adoption is massive. It is used by major tech companies like Apple, Stripe, and even the New York Mets. Furthermore, it is offered as a managed service by all major cloud providers, AWS, Azure, and Google Cloud. To understand Kubernetes, we need to understand its high-level structure. A cluster is the entire set of machines managed by Kubernetes. It consists of two primary components. The control plane, which is the brain of the cluster, it makes global decisions and maintains the desired state of the system. It contains key components like the API server and etcd. Nodes. These are the worker machines, virtual or physical, where your applications actually run. Inside the nodes, we don't just run containers directly, we run pods. A pod is the smallest deployable unit in Kubernetes. It is a group of one or more containers that are scheduled together on the same host. Now the question arises, why do we or why should we use Kubernetes? Because it provides four simple capabilities that manual management cannot even match. First one is declarative configuration. You define the desired state. For example, I want 5 replicas of this web server, and Kubernetes works continuously to maintain that state. Automatic scaling. It can automatically increase or decrease the number of pods based on CPU usage or other metrics. Self-healing. This is critical for uptime. Kubernetes automatically restarts failed containers, replaces unhealthy pods, and reschedules workloads if a node dies. Service discovery and load balancing. It automatically assigns stable DNS names to services and balances traffic across all the run-in pods. Containers and orchestration are not just infrastructure tools. They enable entirely new architectural patterns, hybrid and multi-cloud. They provide a consistent platform to run applications seamlessly across on-premise data centers and multiple public clouds. Cloud native applications. We can build applications designed from the ground up for the dynamic distributed nature of the cloud. CI/CD and GitOps. We can create consistent build environments and use declarative workflows to automate the entire application lifecycle. As soon as you commit or push a code change to Git, we can automate that. It automatically tests if the build is successful and automatically deploys the newer version on your cloud. Microservices. This is the ideal deployment model where each service runs in its own isolated container. Now, as we have touched microservices as a topic, let us go in a detailed view of it. First, let's visualize the difference between the old monolith and modern microservices. In the monolith on the left, you see inventory, payments, search, and users all combined into one big block. If you need to change the search function, you have to redeploy the whole block. In microservices, on the other hand, on the right side, these are split apart. Isolation. Each service runs in its own container. This prevents conflicts. A Go service can run alongside a Python service without issue. Independent scaling. You can scale just one service. For example, if payments is busy, you can add more payments containers without touching the rest of the app. Team autonomy. Different teams can develop and deploy their services independently on their own schedules. Containers are the engine behind modern CI/CD pipelines. The process flows from code, commit, build image, test container, and deploy to production. This approach offers four key advantages. Reproducible builds. The build environment is defined in the Docker file, which eliminates pipeline inconsistencies. Faster testing. Parallel tests can be spun up quickly in isolated containers. Immutable artifacts. The container image that passes testing is the exact same artifact that is deployed to the production. Automated rollouts. Orchestrators enable zero downtime strategies like rolling updates. Now, security is paramount. We must implement security at every stage of the container lifecycle. Image scanning. We must integrate tools into the CI/CD pipeline to scan for known vulnerabilities in dependencies, majorly known as CVEs. Minimal base image. We should use trusted small images like Alpine Linux to reduce the attack surface. Network policies. We use Kubernetes network policies to create firewall rules that restrict traffic between pods so as to uh, control the spreading of the attack. Least privilege. We should always run containers as non-root users with minimal permissions. And at last, secret management. Never hardcode secrets in images. Use the orchestrator's secret management tools instead to set the secrets in environment. Finally, where is this technology heading? The future is evolving rapidly. Serverless containers. Platforms like AWS Fargate and Google Cloud Run combine the simplicity of serverless with the portability of containers, removing the need to manage nodes entirely. Developer experience. Tools are emerging to abstract away the complexity of Kubernetes for developers. WebAssembly or WASM. This is an emerging sandbox runtime that is even lighter and faster to start than containers for certain workloads. It can run directly from your browser on a website. Edge computing. We are now running lightweight containers on smaller devices closer to users in IoT and 5G applications. To wrap up, here are the key takeaways from today's session. Containerization solves fundamental deployment challenges by providing portable, efficient, and consistent units. Docker provides the essential tools to build, share, and run these containers easily. Kubernetes provides the orchestration platform to manage and automate them in production. This shift enables modern architectures like microservices and practices like DevOps. The best way to learn is by building. I highly recommend exploring the official documentation for Docker and Kubernetes at the links provided by the slide. Thank you.